This is the lecture for Module 3 of Unit 2, Colligative Properties. The word colligative is actually a dictionary word depending on number, not kind. In other words, colligative properties are those that increase with the increasing number of solute particles in solution. You have actually already seen one of these in that you have seen that adding a solute to a solvent can lower the vapor pressure of the solvent if an involatile solute is used. A related property to vapor pressure lowering is boiling point elevation, in which adding solute increases the boiling point of a solvent. If a solute lowers the vapor pressure of a solvent, you might anticipate, or you should anticipate, that it also increases the boiling point. You have to raise it to a higher temperature to obtain the vapor pressure of 1 atmosphere. The expression to describe boiling point elevation is straightforward. On the left-hand side here, we have change in temperature, increase in the boiling point. Note that a change in temperature will be the same in Celsius as in Kelvin. On the right-hand side, we have the molality of the solution multiplied by the boiling constant. So the increase in the boiling point will increase as the molality does. Naturally, if you want to know the boiling temperature of the solution, you add this increase to the normal boiling temperature of the pure solvent. So consider the exercise when 46 grams of glycerol was dissolved in 250 grams of water. What is the boiling point of the solution? You can solve this if you know Kb for water, the boiling constant, which is 0.51 Celsius per mole. Now, if you know that, and if you know that water is the solvent because we have more of it than the glycerol, you need only look up the formula for glycerol, and you should be able to attempt this problem before continuing with the presentation. So stop the presentation, attempt, and then continue. We've learned the molality is moles solute per kilogram solvent, so it's necessary to convert the mass of the solvent to kilograms. Mole solute is obtained by dividing the mass of the glycerol by the molar mass. We'll use that as two significant figures for our purposes here. There are 0.48 moles of glycerol, and the 96 grams per mole comes from the molar mass, which is obtained from the formula shown previously. The molality is then moles per kilogram, and we obtain 1.9 molal for that. And the boiling point elevation then is Kb times the molality, or 0.97 Celsius, or in this case 1 degree. And the new boiling point is 100.97, or pretty close to 101 Celsius. This is how glycerol, which is antifreeze, elevates the boiling point of water in the radiator of your car. Another property, a similar property, is freezing point depression. Expression for freezing point depression is very similar to boiling point elevation. Change in the freezing point on the left is equal to the molality of the solution multiplied by a constant on the right hand side. However, in this formula, change in temperature is invariably positive, even though the temperature, the freezing temperature, goes down. It is freezing point depression. Freezing point depression keeps the water in the radiator of your car from freezing when glycerol is added. So we can begin by considering the freezing point of the solution in the previous exercise. Now the freezing constant for water is 1.86 Celsius per mole. And you should be able to use information you've obtained from the previous calculation to solve this problem before continuing. Alright, the solution is that the change is 1.86 Celsius per mole times 1.9 mole, or 3.5 Celsius. And since the freezing point of pure water is 0, the freezing point is now 0 minus 3.5, or negative 3.5 Celsius. Again, when antifreeze is added to the water in your car, it has a higher boiling point, a lower freezing point. It remains liquid over a wide range of temperatures. Freezing point depression phenomena. Well, here's another example of an application in the laboratory. Freezing point depression is used in laboratory experiments to find the molar mass of unknown compounds. For example, consider 12 grams of an unknown dissolved into 200 grams of benzene. The solution freezes at 3.45 C. We know the freezing point of pure benzene solvent, 5.45 C, and Kf for benzene. We can determine the molar mass of this unknown solute. Note that since there's much more benzene than unknown, benzene is again the solvent, and we are depressing the freezing point of the solvent. You have everything you need to know to solve for the molar mass of this unknown. You may attempt that before continuing. Alright, first, 5.45 minus 3.45 is 2. It's important to know the freezing point has been depressed or lowered by 2 Celsius. If we know the freezing point depression in Kf, we can solve for the molality, which is 3.394 molal in this case. 0.394 moles of solute per kilogram of solvent. Multiply the molality by kilograms of solvent and we can determine the moles of solute, which remember is our unknown. 200 grams of benzene is 0.2 kilograms. We have 4 significant figures for 0.2 kilograms of benzene. Multiply the molality, we have 0.079 moles of solute. We can then find molar mass by dividing grams of solute by moles of solute. 12 grams over 0.079 moles gives a molar mass of the solute of 151 grams per mole. Leaving one last example exercise illustrating the importance of the word colligative and colligative properties. Consider adding 20 grams of sodium chloride to half a liter of water. What is the boiling point? Well, we can convert grams of solute to moles as 0.342 moles. Water is our solvent. Half a liter of water has a mass of half a kilogram if we account for the density of water, which is 1 gram per milliliter. So the molality of the solution of sodium chloride is 0.684 moles per kilogram. Now we could go on to complete the problem, find the boiling point of water, but we would be wrong because we have not yet accounted for the fact that sodium chloride breaks into two particles in water. Colligative means number, not kind. It's not important what the particles are, just how many they are. And there are twice as many moles of particles as moles of sodium chloride in this liquid solution. So the effective molality is 0.684 times 2, or 1.37 molal. And the change in the boiling temperature is 0.51 times 1.37, or 0.70 C. So again, we see a boiling point elevation of less than a degree. Colligative properties are in fact a relatively small effect. So in solutions of electrolytes like sodium chloride or other materials, it will be important to take account of the fact that the cations separate from the anions. In particular, for our sodium chloride example, 1 mole of sodium chloride produces 2 moles of particles in solutions, doubling the effect on the boiling point.